So now in this video we're going to look at the 555 timer integrated circuit. This is a circuit that I came up with. The integrated circuit means that within this, generally we call it chips, dual inline package. So there's pins down each side there that straddle a breadboard really nicely. But in any case, there's circuitry within this. We don't have to worry about that circuitry so much, just how the pins interact with the outside world. So we're going to look at that in this video. The circuit that I have here is what I call a Schmitt trigger inverter. And so we have the red LED lit. That tells me the output is high. If I want to set it low, I want to raise the voltage of this trim pot. So this is a variable voltage divider. Right now we are at 6 volts right there. The output is low. And so it's as close to ground as it can be. So it's going the opposite way of the signal we're giving. Now I'm going to turn it when I get to about 1/3 of the way. So this is about 2 volts there. The red LED flips. I can go to 0, whatever. Doesn't matter. I can bounce all around here. I got to work my way back up to 4 volts before the output changes, before it goes low. So from 2/3 to 1/3 of the supply voltage there, that's hysteresis. Whatever we set it in, it'll stay until we overcome that other threshold. So 2/3 threshold, 1/3 threshold. Now we are low at the input, we are high at the output. You can see it heads to ground through the load. And then when we go high at the input, then we are low at the output. You can see it comes from the positive side of the supply through the LED and resistor, and heads to ground through the integrated circuit. We'll look at that up close. To start off with, we have to power the integrated circuit. So pin number 8 is VCC and pin number 1 is ground. You go 1, 2, 3, 4, and then 5, 6, 7, 8. That's the way the numbering system goes with these dual inline package integrated circuits. So 8 to VCC, the positive supply. I have it set to 6 volts. And then pin 1, we will zoom in. So there's some stuff blocking the way. Maybe I can move it. But yeah, you can see pretty good right there. We got the top pin there. Going to the jumper, that goes to ground. You notice here that pin 4 also goes to VCC, the positive supply there. That's waiting for a low voltage, a low input to do what it does. It's the reset pin. It resets the output. We don't want it to reset the output, so we just put it to the positive supply with a jumper. That goes directly from pin 4 to the positive supply. That tells it to do nothing. We have a couple other inputs, and I wrote notes here. So we're giving a voltage to pin 6. You can see that really easy right there. And also to pin 2. That's what the jumper is doing. It's connecting pin 6 and pin 2 directly together. Pin 6 is waiting for more than 2/3 of the supply voltage, 4 volts in this case because we're using a 6 volt power supply. And when you exceed that 2/3 voltage point, it sets the output low. Pin 2 is also looking at this voltage. Since they're tied together, it's waiting for less than 1/3 of the supply voltage, which is 2 volts if you're using 6 volts. And if you go past that threshold there, you go below 1/3 supply voltage, then you will get a high output. So a lower voltage, a high output, and then a higher voltage, a low output for this particular circuit. And here we'll zoom in, so I'll try to move that resistor. You can see that jumper going to the 2nd pin down, and then the 6th pin coming around that way. And that goes right to this jumper there. That goes to the trim pot where we can adjust the voltage to whatever we want. So no current goes in or out of those pins other than maybe a little leakage. They just look at the voltage. So you can go all the way to a supply or the other supply perfectly fine. You're not going to damage anything at this voltage of 6 volts. So now finally we come to the output, and before we actually do that, I'm going to come back and show you with this power supply here. If I bump it, that messes up the power making the board, and it can falsely trigger the 555 timer. So a way to prevent that from happening is to just take a fairly large value capacitor. It'd be best to put it across the power pins right there. Helps hold the voltage. Also pin 5, sometimes you'll see a little capacitor going to ground there too. That also helps stabilize it. But for most demonstration circuits, you can get away without doing that. So in any case, that flip like that because we're in the hysteresis range, if I had it locked into place there. Now I can bump it. It's not going to change, but in the hysteresis range it will. So that's a troubleshooting thing. If you got it falsely triggering, you may need a capacitor across the power supplies, but we're going to keep this video simple, as I said before. So now, also, I got the order for the LED and the resistor opposite. Here I have the, when it comes to the positive supply, the LED before the resistor. There I got the resistor before the LED. Doesn't matter, as long as it's between those 2 points and they're in series. Same with down there. They're in opposite order. But in any case, they are at pin 3, third pin down, 1, 2, 3, that's the output. And right now the output's low. You can see we got more positive, or the blue LED I should say. It's on the more positive side there. So current's flowing through the resistor, the LED, and then it's probably making a really good connection to ground there. It's probably about 0 volts. So we got about 6 volts across that resistor and LED. So now I'm going to turn the trim pot until the red LED lights up. So right now the output is high. So it's as close to 6 volts here. Maybe it's 5 volts. We might lose 1 volt, maybe a little bit more. But in any case, it's as close to 6 volts as it can get. It doesn't get to the positive supply as good as ground. But there you can see now we got the current path through the red LED and the resistor. I'm using a higher value resistor for the blue LED because it's naturally brighter. Less current, it'll be just as bright or brighter than the red LED most of the time. And so 220 ohm resistor to protect the LED right there. And of course, you should really look at those voltages. So I have the oscilloscope there, cable comes out to alligator clips. I just clipped them to jumpers so I can easily move them. It's not connected to anything on the positive side there. So this is our ground. Whatever we see on the screen there will be the voltage in relationship to ground there. It's to the negative supply. So each square here is 1 volt, 1, 2, 3, 4, 5, 6, and that's what we should have at the supply rail right there. We'll look at that really quick, and there you can see it goes up 6 squares. Now we'll go to the trim pot, and actually before when I was demonstrating this I had the power supply set to 5 volts, and I realized that when I first tried shooting the screen. But in any case, there you can see the voltage change as I move the trim pot. So as I said before, if it's 6 volts, we have to wait until we get to 2/3 of the supply voltage, 4 volts, before the output will flip. And there you can see right there we got to 4, it flipped. Now I can go up. Now I can go past that 4, it stays where it is because of hysteresis until we drop below 2 volts, as I mentioned before. So, in any case, we prove that. Now, while the red LED is lit up, we will look at the voltage at the output. So this is where the 2 resistors connect. And there you can see the voltage that we got. It looks like 4.5 right there. So, now I'm going to turn the trim pot, the voltage up at the trim pot to get the output low, and there you can see we got a really solid connection to ground. So it gets to ground really good, but it doesn't do the positive supply, as I said before. So that's more details to read up over time. There's the supply voltage right there, but just be aware of that the output doesn't output as close to the positive rail as it does to the negative rail. And I don't know why we got noise there. Okay, but in any case, I wasn't going to say that's it for the video, but I got my 555 timer from this kit. It's a really common integrated circuit, so I really recommend getting some kind of kit like this, where you got a variety pack of integrated circuits. There's a larger version of this that doesn't cost a terrible amount more. I think this was like $15, and that's like $25 or something like that. I can't remember. But in any case, a kit like that, get those integrated circuits, learn about them, and experiment with them. That's the most fun way to learn electronics, and it's not terribly expensive anymore. So that's really nice. But in any case, that's it. Make sure you check out one of the videos I'm posting. Click like, subscribe, the bell, all that. Donate to Patreon if you can. That helps out the most. I have links down in the description. But just watching videos helps out a ton. I really appreciate that too. I'll see ya in the next video.